recording now?
Yes.
Okay.
Okay. I hope everybody can hear us and see us. It's a pleasure to meet, greet the first of our IEEE Magnetics Distinguished Lecturers, Professor Satoru Emori from Virginia Tech. Professor Emori got his undergrad study done in UC Irvine and then PhD in MIT. Then he worked as a postdoc in Virginia Tech and then joined faculty in 2017. And his primary research interests are in magnetization, dynamics, and spintronics in magnetic thin films. One thing I want to mention before we start, Professor Emori offered to choose from two lectures, one about fundamentals of Gilbert damping in basically magnetic films, and the other one, which is shown here, is more about spin to orbit torque and interplay with magnetic damping in some specially prepared iron nickel alloys. And we decided to show this presentation, but if you have any questions, maybe you may ask also about the other topic, even though it won't be shown explicitly. Okay, please, welcome.
All right. Yeah. Thank you very much, Pavel, for the nice introduction. And I'm very excited and honored to be here in Minnesota, historic stronghold of magnetics research and technological development. So I will say that what I'm about to talk about today, it's still going to have a rather fundamental flavor. So, I mean, I've been an academic for several years. And yet, I do hope that you all have, at least have some fun, going through this particular work with me. All right. Okay, so I'd like to do a little bit of advertisement first. Perhaps I'm kind of preaching to the choir, because I trust that quite a few of you already are members of IEEE Magnetic Society. So if you're not, please consider becoming one. Another thing I wanted to point out is, I'm sure you're all busy and there might be, a lot of restrictions coming from top down the company, but I want to especially highlight this activity right here, the Magnetics Summer School. So this is an annual thing that the Magnetic Society hosts. So a lot of graduate students attend from all over the world. So what I want to say about this is that this is actually, I think this is potentially an excellent opportunity for you all to do some recruiting. So I actually got to go there myself for the first time this summer. This was in Taipei, Taiwan. It was a lot of fun. I was very, very impressed by kind of the caliber and quality of the graduate students who were there. So it's kind of all I wanted to say about the Magnetic Society. I also want to do a bit of advertising about Virginia Tech, or just tell you a little bit about it. So this is where we're located by the Great Appalachian Mountains. And that, of course, means we're surrounded by a great variety of beautiful natural sites, including hiking trails with stunning views, waterfalls, caves with really interesting interiors, and even some breweries that are located in the middle of farms. So yeah, I saw some raised eyebrows here. So I think there's something something of interest for everybody around Virginia Tech. So if you happen to be in the area, just feel free to reach out, etc. So this is a very quick advertisement about what we have been up to in my research group. I won't dwell on this too much, but since Pavel mentioned this other study that I have been giving throughout this tour regarding magnetic damping, so that talk is actually mostly about a paper that we published 4 years ago or so. And this talk has been recorded at least I think a few times. So some version of that is, some versions of those are floating around. This is one that I'm aware of. So, if you're interested, you know, yeah, please feel free to check it out. I believe it's on YouTube. It's a little bit long though, so it's about 1 hour long. Anyway, so finally about well, let's see. I like to take this opportunity to quickly acknowledge both the current and past members of my group. So one thing I want to point out is I forgot to update everybody's year for the graduate students. So, just add one more to each years. So I'd like to especially acknowledge Rachel Mizell, who is our senior most graduate student, who also happens to be one that spearheaded the work that I'm about to show you. So again, if you like what I see, or if you like what I show you today, well, Rachel should be defending in another year or year and a half or so. And although I think she's sort of leaning towards an academic career path, she still may be open to career in industry as well. So please keep her in mind. Okay, so I think that's enough of advertisement, etc. So, like what Pablo said, what I'm going to be talking about today is mostly spin orbit torques, a little bit of damping, but I just want to make sure that we all get started on the same page here. This phenomenon, spin orbit torque, is usually studied in this kind of bilayer structure consisting of what I call a spin orbit material. So let's use a spin orbit material and a ferromagnet. What I mean by a spin orbit material is, well, it's a material with, some strong amount of spin orbit coupling. And to be more specific, we're usually talking about some kind of heavy metal. For example, platinum, tungsten, tantalum, etc. Now, without going into the gory details of so-called spin orbit coupling, the basic idea is that when you run a charge current within the plane of that spin orbit material, you get deflections of these conduction electrons according to their, depending on their preferential spin orientations. So in this simple cartoon, we have rightward oriented red spins going kind of drifting to the top. And on bottom, we have an accumulation of leftward pointing green spins. Okay, so you get opposite spin accumulations on the opposite ends, the opposite surfaces of the material. Now, so this deflection effect, depending on the, based on the spin orientation, this is called the spin Hall effect. Now, from the practical point of view, we like this effect because the accumulation we get, a surface facing the adjacent ferromagnet, can be transferred into that adjacent ferromagnet. So we call that spin transfer. So this is sort of like, so that's a transfer of the accumulated spin angular momentum. And more specifically, this is of technological interest because that spin accumulation or spin transfer can exert a torque on the magnetization within that ferromagnet. Now, there could be different types of torques that can arise from this process, but in this presentation, I'm really just going to focus on one type, what we call the anti-damping or the damping-like spin orbit torque. Right. So this torque, so typically we call it again spin orbit torque because initially that spin accumulation arises from spin orbit coupling within some kind of heavy metal, the spin orbit material. Okay, so now this anti-damping bit, well, as the name suggests, its action is to really is to compensate or cancel the intrinsic damping that's present within the material. Now, from the technological point of view, this anti-damping torque is useful because, as you cancel damping, you get the magnetization to sort of spiral away from the initial direction. And you can with a strong enough anti-damping torque, you can get the magnetization to switch. So that, of course, is useful for switching the magnetization state for digital memory devices. Now, another way in which this anti-damping torque is useful is, well, since we're canceling damping, we can get the magnetization to precess freely about an equilibrium axis. So that can be used to drive a spin torque oscillator. So a high frequency signal generator that is driven by a DC charge current, which again generates this anti-damping torque, letting the magnetization freely process. We can then sort of harvest that dynamics in the form of rapidly oscillating AC signal. So this is a so this is considered to be one promising pathway to make oscillators for not just microwave sources, but for things like neuromorphic brain-inspired computing. Okay. Now, so that's all I'm going to say, I think, for now about the application end of things. Now, from the fundamental end of things, there are different ways in which we can generate that spin accumulation to drive the anti-damping torque. So I have already mentioned the spin Hall effect, which is what's pictured here. There are a bunch of other potentially competing, coexisting effects, such as the Rashba effect. And there are more and more of those, I think, almost every year. Interfacial spin filtering, rotation, and so on and so forth. So my job here is to not really go through every single one of these mechanisms, because I think this gets very overwhelming and confusing quickly. But what I like to point out is sort of the commonality among these potentially different mechanisms. So what's important here, or what's common here, is that for us to get that anti-damping spin orbit torque, we have to somehow transfer that spin accumulation from one material to the other, or somehow the spin accumulation has to cross that interface separating the spin orbit material and the ferromagnet. So in essence, it's an interfacial effect. The spin transfer spin orbit torque, in this sense, is an interfacial effect. Now, there's another sort of consideration that, that makes it even more interfacial in my opinion, which is that once that spin accumulation gets transferred into the ferromagnet, it tends to decay very, very quickly. It decays very sharply within a short distance of about a nanometer or so. So arguably, this is really, really confined near the interface. Okay. Now, because this spin orbit torque, again, is essentially an interfacial effect, of course, by making that ferromagnet thinner and thinner, you are going to get more bang out of the buck, so to speak. So you are going to get more torque acting on, well, more torque per unit moment as you thin down the ferromagnets, thin down the adjacent ferromagnetic layer. You see this sort of simple, 1/thickness scaling, the strength of the torque per moment. So you might think, well, okay, we could just use a very, very thin ferromagnet to enhance the strength of that torque. And in fact, that's what's often done, at least in academia. But this comes at a price, right? So as we thin down the ferromagnet, we actually end up increasing the amount of dissipation that the magnetization experiences. So, we characterize this dissipation through what kind of call an effective damping. So this again shows more of an inverse thickness effect, but sometimes, in some cases, depending on the mechanism of that magnetic relaxation or dissipation, so you actually end up getting higher amount of loss. So you actually end up so you actually end up kind of negating the benefit that you get from the spin orbit torque. So overall, what I'm trying to say is that as we thin down the ferromagnet, you tend to get lossier magnetization dynamics. And this is extremely bad news for developing more efficient and, for example, stable oscillators, and also more power efficient memory devices. Okay, so the main message here is that there's sort of a trade-off between being able to achieve a sizable spin orbit torque and trying to keep the loss of magnetization dynamics to a minimum within the material. So what really got us started along this path is this sort of seemingly greedy goal to achieve both at the same time, both low damping and strong spin orbit torque. So yeah, have your cake and eat it too. Okay, so I didn't really mean to include this. I forgot to delete this particular slide. So when I was in Italy, I was trying to make it sort of relevant to you can kind of get the message. So this is, I think, saying that you can't really have fun with a full cask of wine or something like that. There's another one that that I try to, where I try to entertain audiences in Japan. So the message here is, well, you can have your Kentucky Fried Chicken, not only your fried chicken, but also French fries and biscuits and so on and so forth. Okay, so in this regard, I think our goal is quite modest. We're not trying to get a bunch of different things at the same time. We're just trying to accomplish just these two end goals: low damping and strong spin orbit torque. Okay. So hopefully I've already convinced you that in this sort of traditional scheme where you have a bilayer of a heavy metal and a ferromagnet, it gets extremely difficult or impossible to accomplish both low loss, right, low damping, and strong spin orbit torque. So that's out. Now, so one possible alternative is to just forget about this bilayer structure. So why not, for example, use one single layer of a relatively thick ferromagnet, right? And so another important ingredient is the sort of the recent realization that even in common ferromagnets, transition metal alloys, let's say iron, cobalt, nickel, or alloys, you also have a fairly strong amount of spin-orbit coupling. In fact, that's how we get, let's say transport effects like anisotropic magnetoresistance, anomalous Hall effect. So there's some amount of spin-orbit coupling, and hence something that resembles our good old friend spin Hall effect, right? So this is a somewhat, for some of you, this might sound a little bit counterintuitive, right? Because you might think that when you run a charged current through the ferromagnet, the type of spin polarization that you get would just be collinear, would be just aligned with the local magnetization. But again, the recent realization is that there can be a sufficient amount of spin orbit coupling such that you can get spin polarizations that are always orthogonal to the current direction and not necessarily aligned with the magnetization direction. So it sounds like, if there is such an effect, we should be able to potentially generate a spin orbit torque within the ferromagnet itself without having to transfer excess spins from an outside material. At least that's kind of the simple idea. But of course, we have to think this through carefully, right? Because if we just take a typical ferromagnetic film with presumably a homogeneous composition structure, and this is how we usually try to make our magnetic films, right? So symmetry tells us that even if there is something like a spin Hall effect, the total spin accumulation that you get will just cancel each other out. So equal amounts on top and bottom. So when you look at the entire magnetic medium, you are just not going to get a net spin orbit torque. So this is just not going to work. Now, somebody clever might say, okay, why don't we'll make the top interface and bottom interface, intentionally different, let's say by, interfacing one of those with a, what we might call a spin sink material. So this is material that would sort of intentionally reduce the amount of spin accumulation, causing the spin accumulation to decay just on that surface. Then, of course, you're going to have an imbalance between those two interfaces. You're gonna end up with a net spin accumulation. Hence, you should be able to get a torque. So this would work. However, if you think about it, this is really no different from the bilayer structure, the bilayer scheme that I showed you previously. Really, the only difference is that you're transferring spins from the ferromagnet into a spin sink. The direction is reversed, but really kind of the fundamental limitations are the same, right? So you still have to transfer spin across that interface. So you're going to end up with all those, you're going to end up with the detriment that we had before in the conventional scheme. All right. So what can we do about that? So here's another possibility, which is to intentionally break the symmetry within the ferromagnet itself, so that at least in principle, you are going to have some amount of spin accumulation everywhere within the ferromagnet itself. Right. So this is sort of a simplistic picture, but again, in principle, this is what should happen if there's symmetry breaking everywhere within the ferromagnet. Now we can do this. We can achieve this kind of asymmetry, for example, by intentionally varying the chemical composition in the ferromagnet. Right. So we call this a vertically graded ferromagnet. Okay. And again, in principle, with spin accumulation rising everywhere within the ferromagnet, we ought to be able to generate a torque, again, without having to transfer excess spins from an external material. Okay. So that's the idea, and we like to be able to, we like to say that this was the original idea, but in truth, it was not. So by the time we got started on this particular work, there already were quite a few studies reporting spin orbit torques, in some cases even perpendicular magnetic switching in materials in ferromagnetic alloys with vertical compositional gradients. So these were reported in materials like iron platinum, TMRE, these are transition metal rare earth alloys. However, though, these previously demonstrated materials, they are all very well known or actually infamous for having very, very high damping. Right? So for those of you folks who are familiar with Gilbert damping parameters, these materials typically have damping parameters on the order of, let's say, 0.01 or even greater. So that's about 10 times greater than many of those, let's say, very well-known soft ferromagnets with damping parameters on the order of 0.001. So as it turns out, even though, it is indeed possible to generate spin orbit torques in such materials, iron, platinum, and so forth, they are unfortunately very much unsuitable for low-loss device applications. All right, so again, we come back to this goal of trying to achieve both low damping and a strong spin orbit torque. So in order to pursue this goal, we opted to investigate this particular seemingly simple combination of two ferromagnetic elements. Right. So first of all, we chose iron for due to its very well-known intrinsic damping. In fact, it has the lowest damping among the elemental ferromagnetic metals. And for the other element, we have chosen nickel, which again has the strongest known spin orbit coupling among the three elemental ferromagnets. So low damping. So it's kind of a very simplistic thinking. So what if we combine low damping and strong spin orbit coupling? Do we also get low damping and a strong spin orbit torque? Okay, so let me then walk you through the key materials, the key samples that we focused on in this particular study. So again, our aim here was to investigate the impact of this intentional compositional gradient. So we made this compositionally graded alloy film with a fixed thickness of 10 nanometers. There's really no particular rhyme or reason to why we chose this thickness. It's just a nice round number that is, that's actually relatively thick compared to what many other folks use in the field of spin orbit torques. Okay. Now, and also for good measure, we also had a control sample in which we had no intentional compositional gradient. So here, the composition is supposed to be uniform throughout the film thickness. Right. So at this point, some of you may be wondering why we have this C layer and also a capping layer consisting of titanium and copper. So very quickly, titanium is a kind of a nice adhesion layer. So it kind of allows for the subsequent film layers to stick better to the substrate and go in a smooth fashion. And we also knew from our previous experience that having just even a very thin layer of copper tends to reduce the amount of effective damping, or more technically, the ferromagnetic resonance line width in the ferromagnet. Now, of course, we also have to cap this film, cap each one of these films with something to prevent oxidation. And we also went with copper titanium there in order to preserve the overall symmetry. So this is to say that, well, in this sample series, the only source of symmetry breaking is presumably our compositional gradient here. Right, so otherwise everything else is symmetric. As symmetric as we could make it, at least. Now, one legitimate question at this point is, well, we think these are the films that we are making, but of course, as we sputter all these different elements, it's possible that, you know, what we end up is something completely different from what we intended. But we were able to test that by means of polarized neutron reflectivity. So at this point, I won't really go into the details of how this technique works, but I will just kind of show you the final findings. So polarized neutron reflectometry is a very useful, non-destructive method of probing both the compositional and the magnetic profiles along the film thickness axis. So in the end, what we observe is that for those presumably graded films, nickel iron, iron nickel, we do see the expected compositional and magnetic gradients within the bulk of the film. And finally, in the control sample where we weren't really intending to have any kind of compositional, any kind of gradient within the bulk, again, the polarized neutron reflectometry results indicate, very negligible, almost undetectable amount of compositional and magnetic gradients. So this is to say that the three samples we have here, they do indeed have the structure, at least for the most part, that we intended. All right, so here our claim is that we have a systematic series of samples in which we can investigate the impact of the intentional compositional gradient on the spin orbit torques and low damping. Right, and in fact, so in the subsequent slides, I'm going to walk you through both of these effects. First, the damping. So how does the gradient impact the amount of damping in the ferromagnet? And second, how does the gradient impact the observed spin orbit torque in each of these structures? All right, so let's start out with the damping. Now, before we even started our experimental effort, one concern that I personally had was, well, if we make this magnetic film so, with such a steep compositional gradient, that is to say, when we make a film that is so inhomogeneous, what is really, couldn't that cause the damping to really diverge? Because I think in the field of magnetization dynamics, we often have this intuition that the more perfect and homogeneous the film, we tend to get lower damping. So it sort of seems that it stands to reason, well, when we make the film more homogeneous, the damping should just go through the roof. Right, but I will show you what we actually observe. Okay, so in order to quantify damping, we use the typical method of ferromagnetic resonance, or FMR, which, without going into gory details, is, it's sort of like an absorption spectroscopy where we measure the amount of incident microwave that's absorbed by the sample. Right, so when we hit this resonance condition, when the magnetization is precessing resonantly, maximum cone angle, we see a peak in absorption. And to characterize damping, we look at the breadth of that resonance response, the FMR line width. Now, our standard method is to carry out this kind of resonance spectroscopy at various frequencies. And often what we observe is that the measured FMR line width scales linearly with the frequency. So the standard practice is to take the slope, the measured line width, as a function of frequency, which gives us the parameter that characterizes the strength of damping, what we call the damping parameter. Yeah.
Slightly asymmetric. So is that something which happens only on this particular frequency, or is it something?
Oh, so you're talking about the shape?
Yeah, it's a shape. It's kind of.
Yes. So in general, we do always see some amount of asymmetry, and that just has more to do with, I think, sort of the imperfection in the setup. Yeah, again, you have both, well, let's see. Yeah, so it has something to do with the, let's see, the relative phase between the magnetization precessions and microwave field.
VNA kind of measurement?
It is so we actually don't use a VNA, we use a cheaper technique where we use an RF diode.
Like this, and usually it's like
Yeah.
when you do VNA and account for the phase, it
Right.
can make it symmetric. I was wondering whether
Yeah.
you did it and it's still asymmetric. Okay. So
Right.
that's-
Yeah, so we don't-
that's optional.
Right, but again, yeah, what matters is not so much the shape of it, but yeah, the full width half max resonance spectrum. Okay, so the important message here, so what we ought to be paying attention here is the slope in this data, right? Okay, so for the kind of the boring looking symmetric sample of iron nickel, we get a damping parameter of about, let's say, 4 × 10⁻³ which again, I'll point out is about an order of magnitude lower than the damping parameter that was reported for these previously for these iron platinum transition metal alloys with spin orbit torques arising from compositional gradients. Now the question is, what's going to happen to that damping parameter when we make the composition intentionally inhomogeneous? This is what we see. All right, so we can see that the damping parameter does increase, but maybe about 20% or so. But I think we can live with that, right? So my worry was that it would just really go through the roof. So kind of the good news here is that despite this rather steep gradient, you only get at most 20% increase in the amount of damping in the amount of effective damping. Now, so I haven't really explained what we mean by so-called effective damping so far. What do I mean by effective? What's effective about it? So this is sort of a technical side note that this measured damping parameter includes not only the most celebrated Gilbert damping contribution, but perhaps other kinds of magnetic relaxation contributions. Right, let's say 2 Magnon scattering and so. Well, to address that technical concern, we also carried out FMR in an alternative geometry where we have the sample magnetized out of plane. So this is the geometry in which the non-Gilbert contributions to magnetic relaxation, let's say 2 Magnon scattering, is suppressed. Okay, so again, for the control sample of iron nickel, we obtain a damping parameter. So now we call it the intrinsic damping parameter to emphasize the fact that we really are only picking up the Gilbert contribution to damping. Again, that's about 3 × 10⁻³. And again, quite surprisingly, what we find is that the intrinsic Gilbert damping parameters for the graded samples are essentially indistinguishable. They're basically identical within the experimental uncertainty. 3 ×
Explanation for the offset.
The offset here, yeah, I'll get to that too. So the intrinsic Gilbert damping parameters are essentially identical, but yes, as Pablo pointed out, there's a clear difference in the vertical offset, and tentatively we attribute that to the amount of inhomogeneity that's present in those graded films. So this is in line with sort of the conventional idea that the vertical intersect arises from what's called inhomogeneous spreading. So more inhomogeneous the material, when you extrapolate the line width down to 0 frequency, you tend to get a higher amount of that extrapolated line width. Okay, so this is the quick summary of what we found with regards to damping so far. So when the sample is magnetized within the plane, so that's really our typical device geometry in this kind of a soft ferromagnetic film, while the so-called effective damping does increase with presence of a compositional gradient, doesn't increase all that much, right? And the ultimate damping, the effective damping parameters that we get here are still about an order of magnitude lower than the previously reported graded alloys. So that's good news. And more intriguingly, from the fundamental perspective, the intrinsic Gilbert damping does not appear to be impacted by the presence of this rather steep compositional gradient. We don't really actually have a good explanation as to why that is. So seemingly what matters is really just the global average composition of the material. So this is an open question that we would like to address in the near future. But tentatively, our suspicion is that, well, here we're looking at a length scale or thickness of 10 nanometers. So that's still quite comparable to the ferromagnetic exchange length scale within this alloy film. So our suspicion is that if we were to go thicker and thicker, perhaps we might start to see the magnetization dynamics for iron and nickel start to decouple. But here within the 10 nanometer length scale, it might be that, well, there's enough coupling, right, so that the magnetization, all the magnetic moments along the thickness still process in unison. So in the end, what might matter is just the global average composition of the material. But again, this is all speculative at this point. In any case, from the practical point of view, at this point, we ought to be quite happy because even when we intentionally break symmetry in such a drastic way, we still get a rather low magnitude of effective damping. Okay, so it appears that we accomplished the at least one of our aims to attain or maintain low damping in a symmetry graded ferromagnetic film. Now, what about the spin orbit torque? Right, so before I show you the results, I'd like to sort of motivate all this work with our simple initial hypothesis. So again, our naive understanding is that we should only get a spin orbit torque if there's something asymmetric about the magnetic medium. Right? So this then, stands to reason that when we have opposite compositional gradients, we ought to get opposite polarities, opposite directions of spin orbit torque. Now, a related hypothesis, of course, is in this kind of material structure where, there is really no nominal symmetry breaking, we should have no spin orbit torque. There's just no way we can have an unbound spin accumulation that can generate you a net spin orbit torque. But yeah, let's go ahead and test out this hypothesis. So to do so, we use this experimental technique of what we call spin torque ferromagnetic resonance. So this is exactly like the ferromagnetic resonance technique that I showed you before, but instead of driving the magnetization with a microwave magnetic field, we drive the magnetization with a microwave electric current. In this case, we use a microwave current with frequency of 7 gigahertz. So I'll kind of spare you all the details, but the main message here is that when we measure the rectified DC voltage across the sample, and when the magnetization hits this resonance condition, we end up with this, rather nice-looking resonance spectrum, where we can assign. Well, okay, sorry, I'm not showing you the line width and stuff like that. But the main message here is that when we look at these resonance spectra, well, the polarities of these resonance spectra are opposite to each other. So this is seemingly consistent with our naive hypothesis that the opposite gradients lead to opposite torques, which should then give us these opposite polarities of the resonance response. So that's good. But now the question is, what do we get for that third sample with no compositional gradient? Right, so again, our naive expectation is that we shouldn't see anything. So we should get no spin orbit torque. We shouldn't get any kind of, let's say, classical current-induced torque. So a torque that might arise from Ampere's law, or what we call the Oersted field torque. And yet, we actually do see something. So this resonance spectrum, in fact, or the magnitude of it, is also quite comparable to what we obtained for the other two samples. Well, this is actually quite puzzling. So how on earth can we get really any kind of torques in this symmetric sample, right? Or what we think is a symmetric sample? But okay, so I'm going to sort of digress a little bit because I want to take us back to our initial motivation to achieve a sizable anti-damping torque. So again, there could be different kinds of torques acting in the magnetization, but what we're interested in particularly from the application perspective is the anti-damping spin orbit torque. So there's a fairly simple, although somewhat time-consuming, but conceptually simple way in which we can quantify that anti-damping spin orbit torque. So we make the measurement somewhat more complicated by adding an additional DC bias current on top of the microwave driving current. The idea here is that this DC bias current should generate a DC spin accumulation, or I should say kind of a constant background anti-damping spin orbit torque that effectively changes the FMR line with the overall damping that the magnetization experiences. And indeed, what we see is that the observed FMR line width does change as a function of applied DC bias current. Right? So when we apply DC bias current on one direction, we effectively increase the damping or increase the FMR line width. When we run the DC current in the other direction, we reduce the damping. Now, if you're paying attention to the vertical scale, you might say this is a really, really tiny change. That is because we're rather limited. Our experimental setup really constrained us to a rather small range of DC bias current density. So here we're talking about current density that's, just maybe a few percent of what we actually need to flip the magnetization. But again, we're here to study the fundamentals. We're not yet in the stage of making devices in which we're actually flipping magnetization. So I hope you can all forgive me for that. In any case, the main message here is that this slope, how much the line width changes as a function of DC bias current density, indicates or is proportional to the strength of the anti-damping torque present in the sample. So again, comparing these two samples with opposite compositional gradients, we first of all clearly see opposite direction or opposite slopes. So that of course implies opposite polarities, directions of spin orbit torque. That's consistent with our naive hypothesis. However, already we see something maybe a little bit strange in that the magnitude of the slope is different between these two samples. That's somewhat unexpected, but we're just going to let it slide for now. Okay, now the mystery really thickens when we take a look at, again, our control homogeneous sample, where we still see a slope change in line width versus DC current. So this, again, clearly indicates that there is an anti-damping spin orbit torque present, even in the sample where we have not broken, at least intentionally, any symmetry. Now, one thing I would like to point out, again, the magnitude of the slope also is proportional to the magnitude of the torque. And as you can see, the magnitude of the slope is quite comparable to what we're getting, maybe even a little bit bigger, in fact, than this middle sample, the blue sample, where we do have a compositional gradient. So this is, again, very, very strange. Again, okay, I said something about quantifying the torque, so I'll just try to finish that part really quickly. So in the interest of time, I'm just going to go through it kind of quickly here. So again, my great graduate student, Rachel Meisel, did a very, very careful set of systematic measurements where she did all this, not just at one particular processional axis direction, but over all sorts of in-plane directions. And this is what we ended up getting. So we end up with an angular dependence that's, that appears to be sinusoidal. And it becomes less obvious for the other two samples where the torques, the signal to noise ratio was smaller. Now we'll say, yeah, it's basically sinusoidal. So what does this tell us? So first of all, this tells us that the direction of the spin polarization that's driving the torque is indeed perpendicular to the direction of the current and also within the plane of the film. this implies an effect that is very much like the spin Hall effect that I talked about earlier. Okay. Now, with that in mind, we are then able to assign what's called a spin orbit torque, or quantify what's called a spin orbit torque efficiency. So sometimes called the spin Hall angle. But the point here is that the numbers we end up with here are really nothing to sneeze at, on the order of 5 to 10%. That is all quite comparable to the reported spin Hall angle in traditional bilayer structures, cobalt, iron, boron, platinum, permalloy, platinum, and so on and so forth. So this is, in our opinion, this is quite a substantial or sizable amount of spin orbit torque that we are seeing here. Okay, so now that we're kind of done with all the quantification business, let's get back to the more fundamental question of how does the gradient, well, how should the gradient impact the spin orbit torque? This again is a simple illustration of what we ought to observe. Right. So when we reverse the gradient directions, spin orbit torque direction should be reversed, and we should see zero spin orbit torque when there is no compositional gradient. But what we get in reality looks nothing like what we expected in the beginning. Now, what is especially puzzling to us is, well, why is it that we are observing any kind of torque, anti-damping torque, Oersted field torque, whatever, any kind of torque when there's no compositional gradient? Okay, so again, I'm sort of beating the dead horse here, I think. But yeah, really, how can any torque arise in a presumably symmetric ferromagnetic field? Again, this is a reminder that, if you consider basic symmetry, we should have equal amounts of spin accumulations on top and bottom, and therefore we should have zero net torque. Now, one thing that you might have noticed is, I've been saying something, okay, intentional compositional gradient, and so on and so forth, nominal. What if there was some kind of symmetry breaking that we really did not intend to have within the sample? So one plausible possibility is that, of course, the process of film growth itself is asymmetric. We obviously have to start from the substrate and go upwards. So often what you find is that the interfaces, the two surfaces of a given film layer are not always symmetric. They're not always the same. So often the top layer, for example, is rougher than the bottom. Now, so yeah, that is, I think, more than plausible. In fact, we should expect some kind of asymmetry in general in this case. However, we don't think this is enough to explain what we are observing, because clearly, when we grow a film like this, where the bottom and top compositions are clearly different, well, already the interfaces should be more asymmetric for such a film with an intentional compositional gradient. So again, what we're trying to say is that yes, there is some asymmetry in that nominally homogeneous film structure, but then again, this does not explain why we are getting a torque that is comparable or maybe even somewhat larger than some of these films with an intentional compositional gradient. So even though we cannot completely rule out the scenario, we have to think about an additional contribution that really ought to be the primary contribution to the spin orbit torque, the symmetry breaking. So I already talked about interfaces. So then the only thing that's really left, so if we have interfaces, we also have the bulk, right? So another possibility is that we have some kind of asymmetry within the bulk of the film itself. This can arise, for instance, in the form of residual strain. So this is, again, a very natural and inevitable consequence of growing a thin film on any substrate. So as all these atoms are getting deposited, maybe they are stretching or contracting at different rates compared to the substrate. So you're always going to end up with some amount of residual strain. it's also conceivable that the strain is not entirely uniform along the thickness. Right. So in other words, it's possible that the lattice parameter within the ferromagnetic film is changing ever so slightly along the thickness direction. So this sounds like a legitimate hypothesis, but of course we want to be able to verify it. So can we somehow see the change in lattice parameter directly or experimentally? So you might think, okay, so we could always do something like a cross-sectional transmission electron microscopy. So you would be seeing the lattice structure in real space. So that is one possibility. However, we were worried about, well, so let me take a step back. So the cross-sectional transmission electron microscopy is inherently a destructive technique, right? So there's a very much art to preparing this thinly sliced sample that your electron beam can penetrate. So in that process, in that milling preparation process, it's conceivable that you are destroying the inherent built-in strain within the film. So to that end, we went with an alternative technique that is non-destructive, non-invasive technique of raising incidence X-ray diffraction. So this is a technique that's a little bit like your conventional X-ray diffraction, but we are illuminating the sample, or the incident X-ray beam is coming at the sample at a lower, much lower incidence angle. So we're talking about maybe 1 or 2 degrees or so. Okay. So what is nice about this technique is that by slightly changing the incident X-ray beam incident angle, we allow the X-ray beam to penetrate more deeply into the sample. So by adjusting the incident angle, we can then presumably probe the lattice structure, the lattice parameter at different positions along the thickness axis. Okay, so let's take a look. So this is what this is kind of this is a selection of what we observed for the control sample, 50-50 iron nickel. The peak that we observe here corresponds to the expected face center cubic lattice plane of 220. But the main message here is that, again, by changing the incident X-ray beam incident angle of the X-ray beam, we are probing different positions along the thickness axis. So the higher the angle, the deeper the sample. Now the question is anything changing? So when you just look at it, it's not that obvious, but it does actually become more apparent when we draw a straight vertical line through it. So we can now see that indeed the position of the diffraction peak is changing as we go deeper and deeper into the film. So what this indicates is that indeed the lattice parameter is changing. So the atomic spacing is changing by a measurable amount as we go deeper and deeper into the film. All right, so indeed, so this is more of a systematic plot of how the diffraction peak position changes with the incident angle. And I think this is a little bit more helpful. So this is our ultimate computed lattice parameter as a function of X-ray beam incident angle. So, so this does confirm our suspicion that there is indeed a strain gradient built in within the ferromagnetic film.
The change looks very small to me.
It is. It's not very large. So we're talking about a fraction of a percent. We estimate this to be, okay, the next slide has the number. All right. So yes, I think we're talking about on the order of 0.3% over the thickness of 10 nanometers. But interestingly, when we apply the same technique to the graded samples, we also do see strain gradients. And not so surprisingly, the direction of the gradients are also reversed between those two samples. And yet what's a little bit strange to us is that the magnitude of the strain gradient is actually smaller. Smaller compared to the homogeneous sample. We do not yet know why that is, but at the very least, what what we think we can conclude at this point is that at least in this nominally compositionally symmetric sample of iron nickel, we do have a larger amount of strain gradient than the other two samples. And we think that this is the most likely source of symmetry breaking in this particular film structure. 5 more minutes. Yeah, we're almost there.
Sorry.
Yeah.
Is this, I don't remember, but one, I call 1, 2, 3. 1 and 3 are the same slope. Was it that true also for like line width? 1 and 3 would have the same slope?
Like
Direction? Or?
they do not. So I'll get to that too. Okay. All right. Oh, in fact, yeah, I'm going to answer your question right here. So now that we have obtained the strain gradient within those 3 ferromagnetic films, I think it's a good idea again to see how that result stacks up against the finding, the spin orbit torque, the measured spin orbit torques. So if you just quickly look at it, it kind of looks like they have the same shape, but the signs actually do not match up. So this is to say that, again, while we do believe the strain gradient to be the primary source of symmetry breaking, leading to the spin orbit torque, but that strain gradient alone really cannot explain everything. Right. So there's actually something much more complicated going on. Okay. So just to quickly wrap up here, here's sort of our first order tentative story, although we can see that there are likely many other complicated mechanisms in place. First of all, as far as these 2 compositionally graded films go, at the very least, the polarity of the compositional gradient does account for the polarity, the direction of the spin orbit torque. And for this third sample, we again tentatively attribute the strain gradient to be the primary source of the sizable spin orbit torque. Okay, so I'm almost done here. So again, just as a reminder, we started out this work with the motivation of, achieving both low damping and a fairly strong spin orbit torque in relatively thick ferromagnets. By that, I mean about 10 nanometers in thickness. Now, with regards to the first goal, I believe we were quite successful. We were able to stabilize a low effective damping parameter, even in the presence of rather steep compositional gradients. Now, we were also able to achieve a fairly sizable spin orbit torque. But again, the strange thing about this was that we could attain such a spin orbit torque even without even trying to attain a large symmetry breaking. Right. So again, our conclusion here is that the symmetric iron nickel sample, the spin orbit torque could be explained by the presence of a measurable strain gradient along the thickness, whereas it could be argued that these compositionally graded samples could have potentially competing or coexisting effects contributing to the overall torque. Now, I'd like to conclude just 1 more minute, I think. So I'd like to sort of end this with a sort of broader perspective, what we can learn from this study. So first of all, if the interpretation of our work is actually correct here, it implies that when we have a gradient in structure, not necessarily composition, we can still have a spin orbit torque. So something that's interesting to consider is, well, what if we were to just make a single ferromagnetic layer, just one element, iron, cobalt, or nickel, whatever that may be, and just do we still get a spin orbit torque in such a material, single element material, just by tuning the strain gradient? That's an open question. Now, another important message that we think we can get out of this work is that the conventional picture of how spin orbit torque arises in the bilayer, I wouldn't say it's entirely wrong, but it's likely very much incomplete. Because what we can say for sure from our study is that even if we just have a single layer of ferromagnet with no obvious external spin source or spin sink, we can still get a spin orbit torque. So again, the main message or a big message here is that a ferromagnetic metal film itself can generate its own source of spin accumulation that drives a spin orbit torque in itself. So again, so I think I'm kind of out of time, so I'll just stop right here, and I'm happy to answer any questions in the remaining time.
Yeah, so the key thing here is breaking inversion symmetry. So you could start with a magnetic material that already has broken inversion symmetry, right? And
Right.
profile in that direction. So that should give you spin orbit torques. And I guess conversely, because you break inversion symmetry, you're making your material chiral too, so you get a Ziobrowski-Moria torque. Or at least
Yeah,
it's-
in principle, yeah, that's right, yeah. Inversion symmetry breaking plus, plus spin
Right,
orbit
right.
coupling, yeah,
Yeah.
should get DMI as well.
So if you take something like iron platinum, which already has a pretty strong spin orbit torque, and you grade it,
Yeah,
then you presumably get a large effect, right?
maybe, yeah, so I think from
The
that.
damping is large, of course, but
Right, right. Yeah, so I think there still could be a trade-off. So more spin orbit coupling there is, the larger the damage. Absolutely.
Any questions online?
I'm sorry?
The anisotropy of material. The magnetic anisotropy.
The magnetic anisotropy of this material.
Yeah.
Didn't really look for it, or at least we did, of course, we didn't notice anything within the plane of the film, because one thing I forgot to mention is, well, these are polycrystalline films. And and this is also a rather, soft magnetic material. It's essentially permalloy, but, different composition. So not a particularly, not a particularly strong anisotropy.
We've just got time for one quick question online, if you got one. It's not.
Let's.
Okay. Yeah, thank you all.
Thank you.
Yeah, thank you.
You'll need to turn off recording, just as a reminder.
All right, yeah. Thank you for coming, yeah. Hello.
Thanks, so. Talk.
Yeah.
You, I guess, what is your name, Brianna? Thanks, guys, for something lunch. Yeah. Okay, sure. Yeah.
Yeah, just stop recording. Yeah, it's the button below the one that you just hit. So go to more again. Record and transcribe. Stop recording, top one.